So we've created the poses, and we've got the delta for the pose. We're going to have our process based off using the complete delta, where we apply the pose change before the deformation. There are a number of ways we can build a system out of this, rather than relying on the data as we're creating it within the network. Generally, the best approach is to use external files. We can then use these files to create a pose library which is cached within the scene. It is also possible to convert these poses to attributes, and we can then store multiple attributes in a single file. But essentially we want to be able to store our poses so that we can swap them out and we can update and change them without fundamentally breaking the rig. We also want a system that is easy to back up and one which is robust against loss of data if a file gets corrupted. Another advantage of making sure we save everything as an external file is that we will always have a base for deformation. So we do not have to rely on animation within the scene. As long as we know the angles for the pose, storing that pose externally means that we can always further update that pose. So to export the positions we would want for an updated pose, we need a couple of things. I'll start by getting a ROP geometry node. Here we would want to export our final character mesh before any of the deformation is applied, but after we have all of our attributes. This is one of those things which is just a good idea, and we always want our base geometry. However, for the pose itself, this is actually unnecessary, because in this case what we really need to have is the bone deformed data, and the bone deformed data in the position where the bone is actually deformed. We would actually export this in two variants. The first would be a ROP geometry output. This will be connected to my deformation. We'll do this to export the deformed position of the mesh, along with all the relative information we need for that position. These will be stored in attributes, and the bgo.sc file will retain these attributes. I'll call this file pose.bgo.sc. In this case, I will not put any information into the file name. However, with this kind of file, it is usually best to specify which joints are bending and by how many degrees. So in this case, it would probably be elbow 90. In this case, I'm also going to be exporting using a file node. This is to export in a format I can use in external applications. In this case, ZBrush. I do not have to export for ZBrush. We can also use plugins for this. These are Labs plugins. Here we have two GoZ nodes, one for import and one for export. We'll look at these later. However, in many ways I do prefer using an OBJ file. This is just more robust. Live links are useful for working dynamically, where storing the poses as files are not as good for interactivity, but they are better in terms of robustness and storage, and they're much better for libraries and archiving. If a plugin gets updated, it may corrupt data. This is not a problem which you'll have with a file. I'll specify the file name as pose.obj. I'll also need to specify a proper path for this. In this case, I'll be saving this locally to my project under a folder called geo. I will change the file node to write files. With the ROP geometry node, I can save to disk. The file node is a bit more esoteric, as we do not explicitly write the file. To do this, we need to display the file node as the final output of the network. So I now have my pose exported and I can work with it. So in ZBrush, I can import the geometry. This will import the OBJ file. I should then be able to edit the geometry. Once again, this is going to be very sloppy modeling, but it should serve as an example. So basically, we've got our changes within our subtool. We can make sure we have the correct subtool selected, and then we can export. I'll call this updated pose. So that would be a straightforward file export from ZBrush. The other option is to use the GoZ plugins. I'll not cover the initialization of the plugin. I'll get the GoZ export node. I'll plug the deformation into this node. I can then send to ZBrush. I should be able to draw my geometry into the scene. And I'll then edit it. We should then be able to use the GoZ button. This should send the updated geometry back to Houdini. If this is working correctly, we should generate a GoZ node. So this is a far more intuitive way of working. However, in the long term, it is usually best to export the final file once you've finished with this, as cache data is always a little bit more likely to be corrupted. You also have the problems of updates between software, so there may be updates to ZBrush, Houdini, or the plugin. Usually this will not be a problem, and if you saved your scenes correctly, you should have no issues, but individual files are still a better way of storing information. So that will give us the deformed geometry directly from ZBrush. I can also get a file node, and we can import our modified file. Finally, I want to get another file node, and I'm going to get our original pose that we stored in the bjo.sc file. So this will allow us to set up a pose library independently of the main network. So we're going to use the original file, and we're going to use our updated file. And we'll pass this into the attribute wrangle where we process the inverted matrix. The second input will be set by the original file. The first input will be set by our pose. This will give us the delta transform as applied to the original mesh. This will work for the GoZ import as well as the imported file. So this way we can use the exported data to set up a pose library, and we can then reapply this library to the mesh. So we could isolate this entire process to the setup process. We could then export the poses as highly simplified meshes or as point cloud data. This would allow us to remove the pose creation from the final rig entirely. So now we could connect these finalized poses to the network. We would do this with a blend pose. So once again, this method works best if we're connecting this before the deformer. The first input will be my mesh. Our poses can then be fed into the multiport. We'll then update the node using the update channel names from inputs button. We should now be able to blend our delta with the mesh. We'll now want these parameters to work with our deformation, so we want to automate the implementation of the blend pose. I'll go through a couple of ways of doing this. Generally speaking, there are quite a few approaches which you can take. These will depend on the type of rig which you have and the complexity of the rig. So what we're going to do now is we're going to drive this pose slider here so that it matches with the animation. So we want to be able to animate the blend pose in concert with the deformation. I'll only be performing a linear blend. Generally, you'd want to augment this with curves, and you may actually want to blend through multiple poses. We'll start with the most straightforward way of performing this. This method will use information from within our pose node. This method works best if we have a rest pose, so I'll get a stash pose node. This means that we'll calculate our transformations based on a specific static pose. I'll store this pose with a rig stash pose node. I'll connect this between my rig doctor node and the pose. I'll store the rig based off the default skeleton, and by default this will create a rest transform. So we're going to work with the rest transform, so we will not pre-multiply by the incoming pose. Instead, I'm going to calculate my rotations based off my rest pose. The mode will be set to from rest pose. I can then go to the settings tab in the rig pose node. There are two options here where we can generate extra attributes. These will be the toggle for parameter attributes and the toggle for internal attributes. In this case, we need the parameter attributes. We do not actually need the internal attributes, but we can use these. We can use the local transform to actually get the information, but that is not a method which I'm going to be exploring. In this case, I'll be activating the parameter rotates. This will store our rotation values as an attribute. We can look at this in the geometry spreadsheet. Here we will have a vector attribute called R. This vector will store our rotation values. These are the rotation parameters for each of the joints as they are set up in this pose node. Note that this is not a total rotation. It is specifically the rotation from within this node, which is why this works best when it's based off a rest transform. This technique is not the best when we're using motion capture, as using the rest pose will override the inputs of the pose node, so this is not a good option if we want to use motion capture or re-rig an animation. Since this is stored in an attribute, it's very easy to implement. We can select the blend node, and we go to set an expression in the parameter. This is a point expression, so we'll use the point function. We'll fetch the attribute from the rig pose node. So this will be a string, .. rig pose, and in this case I'm using rig pose 6. The attribute that we're looking for is R. The last argument will be the index from the array, In this case, I'm rotating around the x-axis, so this will be 0. I get an error because I forgot to set the point number. The second argument should actually be the point number, and this should be 1, because this is the point which I'm currently animating. We should now have deformation, but this deformation is very extreme. This is because we will need to normalize deformation. Currently, we're overshooting the deformation by a long way. By default, we should be moving the slider between 0 and 1. So to normalize this, it is pretty straightforward. We'll divide the results of the function by the angle at which we want the most deformation. In this case, I've set the deformation to be at 90 degrees, so I'll divide this by 90. Our deformation should now work in tandem with our animation. Now we'll look at a way of dealing this which will work better with motion capture, and this is a way which we can approach using VOPs. The final way we'll look at things will use VEX, and will be more robust than this, but this will show an approach to doing this with VOPs. For this, I'll start by getting a pose difference node. The pose difference node will give us a delta between two poses. Basically, it will give us the movements required in a rig to move from one pose to another. Essentially, this is just the difference in the poses. By default, this will store the pose in an attribute called offset. I'll set the second input with a pose before we store any animation. The first input will store my animated skeleton, and this will be set by the pose node. So in the geometry spreadsheet, we should be able to see an offset value, and this will be a 4x4 matrix. This is where we'll store the delta. I'll update some of the parameters in this node. I'll set the transform that we're looking for to be the local transform. We'll then need to associate our points with each other. The most reliable method is to map by name. However, mapping by point number should be faster. In this case, the numbers will line up exactly. So I'll associate the points from each input with each other using the point number. We can now get our difference using this offset attribute. First, we'll do this using VOPs. This is one of the cases where using VOPs is actually a lot easier than using VEX. Mainly because the VEX function for this is a little bit obtuse and a little bit obscure. It is also one of the functions which doesn't have the best documentation. I'll connect the rig attribute VOP to the pose difference node. We can then enter this VOP. In this case, I'm not looking for any of the rig information. Instead, I'm looking for my attribute. So we'll use a get attribute node. The offset attribute is a 4x4 matrix. So the signature should be as a matrix 4. We're passing our geometry into our first input, and this is a point attribute. The attribute that we're looking for is our offset. Once again, this is the name of the attribute which is specified in the pose difference. We could rename this attribute at any point. So next we'll want to get a rotation in degrees from this offset. And to do this, I'm going to use an extract transform node. I'll pass my transform into this node. What we want to do now is we want to get the rotation from this node, and we want to add this to our geometry as an attribute. To do this, we'll use the set attribute node. We'll set the value of the attribute with our rotation. To see the result, I'll open the geometry spreadsheet. I can change the name of this attribute to be R, and I'll set this attribute to be on point 1. I've already got an expression with R as a value, so I'll change this to RO just to be more clear. Currently, we're still generating the R attribute within the pose node. I'll deactivate the options for that in the settings tab. So now we have an attribute for the rotation, and we can use this in exactly the same way. I'll update the point expression. Instead of specifying the rig pose, we'll specify the rig attribute VOP. I'll update the attribute that we're looking for to RO. So we may also want to take this approach using VEX. We'll look at this quickly using an attribute wrangle node. Once again, I'm going to be using a vector attribute to get a rotation. I'll create this attribute with 3 at rot. And this will be set using the crack transform function. This is a function which I think is poorly documented. You can figure out how to use this function from the documentation, but this is not particularly clear. There is no real explanation of either the TRS argument or the XYZ argument, and really you will only figure out how to get these working by using the note, which ironically is not actually meant as an explanation. The first value will be xform underscore TRS. The second value will be xform XYZ. The next value will specify whether this is translation, rotation, scaling, or shearing, and this value will be 1, which will give us a rotation. This will be followed by an empty vector, and then we will have the matrix which we're getting the values from. In this case, it will be the offset attribute. I'll need to specify that this is a 4x4 matrix by preceding it with a 4. We should now be able to update our point function. This will now refer to the attribute wrangle node. The attribute that we'll now calculate the rotation of will be rot. One thing to be aware of is because we're working with matrices, we cannot always predict what angle we'll get from this. In certain cases you may get flipping, and you may need to reverse the way we're calculating the angle. That, however, will be on a case-to-case basis, and is something which can be easily compensated for. Now I'm showing the final method which I'd use to calculate the angle. This may well be the most robust, but it is also the most technical, as we will need to do the actual mathematics of the calculation of the angle. This is something which I will only do in VEX, although it's reasonably straightforward to do in VOPs as well. I'm going to calculate the angles between these joints based off their transformations. In this case, I'm going to get vectors based off the transformations, but we can actually construct the vectors by subtracting the positions of the points. So we'll look at the transforms. I'll scale the visualizations of my transforms so they're easier to see. So for this rig, the axis that is pointing down the length of the bone is the y-axis. So I can use the y-axis as a vector to get the direction of each of these bones. I can then calculate the rotation as the angle between the vectors. So I'll need to get my transform. I'll store this in a variable t1, and this should be a 3x3 matrix. This will be a point attribute, so we'll use the point function. The input geometry is from our first input, so this will be 0. The attribute that we're looking for is the transform attribute. I'll get this from my first point, so this will be point 0. I'll need this for the point which I'm transforming as well, so I'll duplicate this line. I'll call this variable t2, and I'll get this transform from point 1. These should be matrices and not vectors, so the type should be matrix 3. Next I want to get my direction vectors, which in this case will be the y vectors. These will be stored in vector variables. I'll call the first of these y1. I'll set this with my first transform. The x value will be t1.yx. Then we'll have t1.yy and t1.yz. I will duplicate this line. This variable will be y2, and it will be set with t2.yx, t2.yy, and t2.yz. So that will give us two vectors. In this case, the vectors are from transforms, and this means that the vectors should already be normalized. Calculating the angles between vectors is far easier if the vectors are already normalized, as it simplifies the equation a lot. This is because the equation requires multiplication by both of the vectors' lengths. If the length is 1, then we do not have to bother with that. This is also a case where normalizing the vector may actually be computationally cheaper than calculating the length of the vectors. So here, if you were calculating the vectors manually, I would normalize them. So I'm going to store this in an attribute. This will be a float attribute, and I'll call it angle. So the simplified version of this equation will be to get the arc cosine of the dot product of the two vectors. So we'll use the acos function. We'll then want the dot product of the normalized vectors. So we'll use the dot function, and the vectors will be y1 and y2. We can then look at our values, and we have a value for our angle. In this case, it is 1.5708. This is nowhere near the angle that we want. The reason for this is that this angle is in radians, so we'll need to convert our result to degrees. I'll do this with the degrees function. We should now have a 90-degree angle. I can then check that my angle is actually being set dynamically. So in this case, we should now be able to use this to set our angle. We'll need to set this function to reference the attribute wrangle node. And we'll set the attribute to be angle. and we should now be driving our pose by calculating the angle. We now have a number of ways of calculating the angle between our joints. I have also covered storing poses, as well as controlling the transforms of poses based off angles, and this should allow you to create complex pose space deformation setups.